looks like we're all here. So I know you're all really excited to be in this room for another hour or so. So just want to start off by saying thanks for having us again. We are OTB Engineering. We're very happy to be returning here to MIT to show you our final proposal for a pedestrian bridge in North Point Park. This is, Good? There we go. We're OTB Engineering, as I was saying, and we're here to present to you our final proposal for a pedestrian bridge in North Point Park. It's been a grueling 6 months of design, but the bridge that you are seeing here for the first time in public is a one-of-a-kind bridge. Our researchers have looked far and wide for a bridge that is a cable-stayed bridge, merged with a pontoon bridge, that rotates open. There is no bridge like this in the world. It is certainly the most exciting and innovative bridge to hit the New England area in decades. And we're very, very excited to tell you about it. First, let us introduce you to a little bit about our company. You might notice some of our work here. Some of it's very famous, and we've received many accolades over the years as far as our bridges. Our bridges, they're beautiful, they're serviceable, they're innovative, they're cutting edge. And people often come up to me and they say, Medio, how you guys doing? You guys are doing great over there, you're hitting it out of the ballpark. And I say, well guys, one thing we have here at OTB Engineering, it's kind of a funny phrase, but we like to have, in our bridges, sex appeal. That's right, all our bridges are sexy. And I'll tell you one thing, the only thing that's sexier than the bridges that we make are the people you see out in front of you here today. I don't need to back that claim up, you guys can see that for yourselves. And I'll tell you one more thing, these aren't just a group of well-dressed individuals who look good. They are the best engineers that OTB has to offer, and I would say the best bridge engineers in the world. And it gives me great pleasure right now to introduce you to our team and what we're going to be talking about today. I'll start off with myself. Go ahead, get it out. My name's Medio. I'm CEO of OTB Engineering. I'm here today to introduce to our staff and our static design procedures. I know, it's great, right? Everybody, please give a warm bonjour or guten tag to our head of all European operations, Dr. Roman Medio. He's going to be taking you through our architectural concepts, as well as the dynamic behavior of this bridge. Everybody, please give a warm marhaba to this beautiful Habib Dana who's here today to talk to you about the connections on our bridge. And she is also the Middle Eastern head official for OTB Engineering. He's back, Dr. Hang Lee. Everybody, please give a warm ni hao. He's here today to take you through our construction schedule. And last, but certainly not least, everybody please give him a warm American hello to our head of U.S. operations, Sir Trevor T. Burton, who's here today to take you through the erection sequence as well as the value engineering we perform for this bridge. I'm not going to hold us up anymore. I'm very excited. I know you guys are. Dr. Juan Neal, take it away.
Thank you. So I will present you the architectural concept for this bridge, and I will first show you this video. So our initial concept was to do a bridge as lightweight as possible to actually not have a significant impact on the view over the park and the river. And we were interested in having this view that the cables that fades in the middle, and that gives this impression that you're maybe on a ship where you're surrounded by cables and you're very close to the water. So that's the idea that behind this. And we were thinking that maybe with playing with details and cladding, we could enhance this feeling. And so, for example, if you use a timber cladding, you will have this very nice feeling. I know that the water is a bit too blue to be in Boston. You can it's a rendering issue, but you get the feeling of what it is to be on that bridge. Here you see from a general perspective that the bridge is very lightweight, and something that is interesting on the idea of being on a boat is that you have actually these pontoons that you barely see here, so the bridge is actually also floating like a boat, and it's moving over the water, so because it rotates around these points here and here. And finally, I want to show you this general image of the connection details. They're very clean, they were designed by Dana's department. And you see that the slenderness of the bridge and the expressivity of the structure. And now we hand it again to Emilio, who will talk a bit more about the structural design.
Thanks, Roman. Okay, so as Roman just showed you, we are looking for a very slender design in this bridge. So we originally said we need to have cables that are not chunky, and the same with the pylons, because that's just going to take away from the whole thing. So we started off with our static design, saying let's analyzed the whole bridge as an analytical model. So we reduced everything down to a beam on elastic foundations, equating the cables to equivalent springs and doing the same with the pontoons. And the results of this analytical model showed us two things. First, the cable sizes would be not too chunky. We were very happy with that. The second thing was serviceability was going to be a big thing for this bridge. It's a very long span, and to meet serviceability requirements at the midpoint, the pontoons were more than necessary. So we took the results of this analytical model and we inserted it into our finite element model. And for this project, we're using General Structural Analysis, or GSA, by the company Air. It's a very good software program, and as you can see, this is our first finite element model right here. Now, what we wanted to do was we wanted to camber the deck using pre-tensioning on the main span cables. To reduce some variability, because we were doing this heuristically, to reduce some variability in the three-dimensionality of the structure, we pinned the pylon at the top originally and started heuristically pulling on the cables until, under dead load conditions, the deck was flat. And then we released the pin, and that's when things got fun. Because we were having huge deflections at the midspan, unacceptable deflections. So we said, what's going on here? Why isn't it not matching the analytical model? And what was happening was, in the analytical model, we had assumed that the backspan cable would be adequately stiff enough to avoid the phenomenon that you're seeing on the screen right now, where the pylon deflects towards the main span and causes a rotation of the pylon, which causes a huge deflection at the deck. So what did we do? We said, well, we got to go back to the drawing board. We got to see what size cable do we need in that backspan to actually avoid this situation right here. So we ended up going from a 3-inch diameter cable to an over 5-inch diameter cable. At which point, I don't know what to do, so I call Donna. I say, hey, listen, Donna, what do we got to do here? Like, can we do this 5-inch cable? She says, sure. But you're going to have like a 2-ton connection, clevis up at the top, and it's just going to look really chunky. I'm like, that's not my MO on this project, all right? We're trying to do something really sleek. So what can you do for me, Donna? And she and her crew over there, they're the best. They always get me out of my jams like this. And what they did was, they came up with this connection right here, where she said, listen, we'll use 4 cables instead of 1. We'll break it up into 4, we'll get the same amount of stiffness, but now it's still going to be transparent and beautiful. And that was a home run for us. We went back to the Ernst equation, which to adequately pre-stress our main span cables. We also went and said, hey, let's incline the pylon back to get a little bit of help from its self-weight and add some more pontoon springs. The pontoons are more than necessary on this bridge. They're what achieves serviceability for us and attract up to 20 to 30% of the load on certain load cases. So with that, as you can see here, this is a one-to-one renditioning of the deflected shape of our bridge. We're meeting, the sag of the cables is hardly noticeable, and we're meeting our midspan criteria for deflection. So with that, we had our cable sizes, and they were more than adequate. It was time to move on and see what kind of size pylon we would need for this project. Now, from the beginning, as Ramon mentioned, we are rotating this bridge using hydraulic jacks and rotating it as such. Under closed conditions, we're talking about cables and pylons that are in the same plane, which means that all the pylons will be in pure axial compression. But we knew from day one that things are going to get a little higgledy-piggledy when we rotate this bridge and everything's not in the same plane. Because we're going to be pumping in some serious moment into these pylons. And as you can see here, this is the finite element model closed, and this is it when it's open. And we are pumping in about 2,000 kick-foot into this pylon. It is what governed the design of the pylon. They ended up being a diameter of 32 inches and about 1 inch thick pylons, which were still very slender and we were very happy with. Now that we had the main components of the bridge sized, it was time to make a full-scale model. So we mirrored the model, and we talked to Donna about what kind of conditions she wanted her connection to be able to carry here. We inserted them, and then we used this full the static analysis case to get down all her load cases for all of her connections. And then we went ahead, we set up some modal analyses and some football analyses, and we said, okay, Roman, go for it. And he's going to take you through the dynamic analysis.
Thank you. So for a few minutes, I will pretend to be Professor Connor and explain you the design methodology that we use for the dynamics. When you think of dynamics and footbridges, you think of vibrations that is induced by the pedestrians. And you have 2 things that can occur when you have vibration. The first thing is actually what occurs for a Tacoma bridge. It's not a pedestrian bridge, but you can have collapse due to vibrations. And if you think of that, it's what Professor Connors calls the strength-based design. But on the other end, you have also vibrations that won't provoke the collapse of the structure, but that will provoke motion sickness, or even people can notice the motion and freak out and start walking on the structure. And so if you want to avoid that kind of phenomenon, it's called motion-based design. And generally that occurs for very slender, very lightweight bridges, and our bridge is in this second configuration. So what do we need to design the footbridge from motion-based? So we have to define traffic classes, so define how many people go on the bridge, how often that occurs. We have to define comfort evaluation for people, and we do that through literature review based on comfort and acceleration. And together with the client, we define the performance objective for the structure, and we try to link the traffic and the comfort. So on the traffic classes, this is maybe what a bridge looks like 99% of the time. There's barely no one on there. From time to time, you might get a bit more people on it, and very rarely you have this kind of event where the bridge is fully packed. So with that, we define, actually we found in the literature 5 traffic classes, from very weak traffic to exceptionally dense traffic. And we found 3 different classes of comfort, and actually the very weak and weak traffic maybe occurs 95% of the time. So we decided that people should have the maximum comfort for this case. And for rarer events, we choose to have medium or low comfort on the structure. So other assumptions, because damping is actually it's theoretic and not viscous in real structures, it depends on the amplitude of the oscillations. And if for seismic we design steel bridges with 2% damping, for comfort you have actually to take a very lower damping ratio and you go down to 0.5%. And finally we had to find what are the critical frequency of human walk, and we found in the literature that it's between 1.2 and 2.3 hertz for vertical modes, and because for horizontal modes, normal people actually alternate left and right foot. You get divide by 2. So with that, we went through a model analysis of the structure with the idea of having 90% of the effective mass that would be calculated. So we needed 40 modes for that. But actually, for the critical frequency that we showed you, we only have a few modes. The first one are actually rocking of the pylon, so they are not relevant for the crowd-structure interaction and won't actually have any significant impact on the design for comfort. The third mode is interesting because here you get an horizontal mode that is within the range of critical frequency. It's fully horizontal, and we will have to take care of this one. Just a remark here, we have already with the 3 first mode 70% of the mass for effective mass, and for horizontal, and the frequency are still very low, so we think that for earthquake design we won't have any problem with this bridge. And we had finally 3 vertical modes that are in the critical range of frequencies, so you see this kind of global modes of the decks, and so we had to take care of that more carefully with a footfall analysis. So within the footfall analysis, you specify a number of pedestrians, and you input the nodes that you want to excite, so the deck obviously, and you will get an acceleration, and you will get the maximum value for acceleration and displacement. And actually it turns out that the vertical modes are okay for design criterion, but that the first horizontal mode is a problem. So we had to do something for that. And our first idea was to maybe stiffen the structure, but the mode frequency is so low that we would have needed to have a very chunky structure that was not compatible with our architectural idea. So we had to find a passive damping solution, and more specifically a TMD, so or tube mass damper. So the idea is that if you have a single degree of freedom system, you can excite it to its resonant frequency, and you will get a huge response. But if you had another system that are the same frequency, when you will move this system, you will actually also excite this one, and this system will pump the kinetic energy out of this. And if you add a damper between these 2 elements, you will actually dissipate this kinetic energy that you from the